Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello friends. So in this lecture we are going to see how fire affects structural systems. So basically we are going to look at how fire acts as a structural load. Now from a qualitative perspective, fire applies load in a very different way as compared to other loads that you may be familiar with, such as dead loads, live loads, wind loads, etc. So in characterization of fire loads, there are few terms which we need to discuss. First thing is fire load. Okay. So basically the total amount of combustibles in a space which is in energy units. So the total amount of energy that will be released when combustion happens, that is effectively termed as the fire load. Now how this fire load affects structural systems depends on a large number of conditions. One obviously is the total amount of fire load, which means total amount of energy which is in joules or megajoules, right. Then second is the configuration of the compartment or the building itself. How that affects fire will be whether a fire is fast growing, whether it is slow growing, and how severe it is. So the severity of fire, or in terms of characterization, behavior of fire, that is typically characterized in two ways. One is called HRR versus time, which stands for heat release rate versus time, and second is a temperature versus time relation. Okay. So here HRR stands for heat release rate. Once we have characterized the fire itself, then we begin to do calculations of structural temperatures, which means the room temperature is known in terms of the fire temperature or the time versus temperature graph. Now using that, we need to be able to calculate the structural temperatures. Okay? And the knowledge about structural temperatures eventually lead us to enable calculation of structural fire ratings. Okay? And we will discuss about how these ratings are defined. So as we said, what is a fire load? Anything that can burn. So this includes furniture. It is the most common fire load, typically comprising of wood and fabric. It can comprise also of appliances such as plastic chassis bodies, right, like toasters sometimes. And we said that they are characterized in terms of energy units, which is joules or calories. In the SI system, we typically use joules to measure energy. Okay. However, for a given space, only the absolute amount of energy does not give a complete picture. So for example, we can have 1000 kilojoules of energy, which is located in a very small room of say 3 by 3 meters plan dimensions, and the same amount of fire load, which is 1000 megajoules, it is located in a very large room of say 10 by 10 meters. In both these cases, the severity and intensity will be quite different. Hence, we define another term which is called fire load energy density. It is simply the total energy contents divided by the area. Okay? And this area sometimes is AT, which is the total internal area, and sometimes is only AF, which is the floor area. The usage depends on the context, but the general idea remains the same. That is, we want the density, which is energy per square meter. Okay? And we have already discussed that it represents the total amount of energy that can be released in the event of a fire. So, in estimating how the total amount of energy will be, we need to know amount of fire load, which is this fire load energy density, and also we need to know the geometry of the rooms, opening sizes and location of the openings, because as you have seen previously in the same course, that fire triangle or fire tetrahedral, all the components are necessary for a fire to sustain. So the geometry of the rooms, size of the opening and location of the openings will define whether sufficient amount of air or oxygen will be available. Before we proceed towards actual calculations, it will be good to get some idea about physical interpretation of energy, or how much energy is too much energy. Right? So 1 joule of energy, or that order of magnitude, is the energy or the kinetic energy possessed by a person who is of an average weight, less than average weight, moving at a very slow speed. Okay. Then 1 cup of rice that we eat, that has the energy in terms of kilojoules, or the order of magnitude becomes kilojoules. 1 megajoule is same as 1 kilowatt hour of electricity that we consume, which is 1 unit of energy in terms of electrical energy. Okay. Alternatively, if we burn 1 kilogram of food completely, it releases about 17 megajoules of energy. And we will see that this particular quantity, which is the energy released per unit mass, is also called the calorific value of a material. Then when we go to gigajoule scale, then we are discussing or talking about 1 barrel of petroleum which is burning. Okay, so in total it will release about 6 gigajoules of energy. Most of the discussions with respect to fire engineering are remaining within the gigajoule scale. Okay, so gigajoule or megajoule scales. Terajoule is an extremely large amount of energy. So to get a sense, one of the nuclear weapons that was used, it released about 63 terajoules of energy. So if m is the mass of a combustible item, okay, and c is the calorific value, then the total energy E can be simply written as m times c. So this is the total amount of energy that will be released when this amount of material is burnt. Okay. And when this total energy is divided by the area of the floor or total internal area, that becomes small e, which is the FLED or the fire load energy density. In a similar way, we can also discuss in how much time this energy has been released. So when we divide the total amount of energy released by the total amount of time it has taken, that is what is called heat release rate or HRR. So HRR, we can say average HRR is equal to the total amount of energy E divided by the time T. The time T is what it has taken for combustion. The units of this average HRR will be the units of power or joules per second or watts. Okay. So watts, and generally the magnitudes are such that we measure in kilowatts or megawatts, is the energy release rate or heat release rate of a fire. Just like we divided the total energy by area to obtain a fire load energy density, if we divide the total amount of heat received at a surface by the area, that gives heat release rate per unit area. Okay. And the units will be in watts per square meter, and we will see that several software, this HRR PUA is an input that is required to be given to calculate the overall fire dynamics. Now, the one question one may ask is that from where do we get calorific values of common materials? So most of the building codes, including the National Building Code of India, has tabulated these values. Okay. So this table 9 of NBC part 4 gives calorific values of common materials. So we will see that here one of the columns is materials. Okay. It is classified based on whether it's a solid fuel, is it a hydrocarbon or other common solids or even foodstuffs. Then this column number 3 gives calorific value in megajoules per kg. Okay, so this is column is multiplied by 10 to the power 3 and the unit is given as joules, kilojoules per kg. So effectively this is megajoules per kg. Okay, and the last column gives wood equivalent, which is kg per kg, which means how much wood would have been burnt to obtain the same amount of total energy. So let us look at it from an example. So a storage room has 100 kilogram of cellulosic material which is stored. So cellulosic material is basically wood or paper or materials which contain a lot of cellulose. Okay. Now we want to ask that what is the average HRR, average heat release rate during a fire incident which lasted for say 45 minutes. Okay. So what we are told is this was the amount of cellulosic material available and the total time of burn was 45 minutes. So how much is the average heat release rate? So first we calculate the total energy where we get this 100 kilograms of the material multiplied by 17.6 kilogram per kg, which is the calorific value of wood. Okay, so that we have taken from this table. So this 17.6 megajoule per kg. Okay, so the total energy content comes out to 1760 megajoules. Now this megajoule we divide by the total amount of seconds, which is the time. Okay, so time is 45 minutes, so 45 times 60 seconds. So overall we get an average heat release rate of 651 kilowatt, or in other words we can also write it as 0.6 megawatt. Now one thing to notice in this is that if we were to draw a graph between heat release rate and time, okay, since here we have assumed a constant rate of burning, that is what this average HRR gives, the graph would look like a straight line, okay, where this end time is 45 minutes and this is average HRR, which we have calculated to be 651 kilowatts. Okay. So this is how the heat release rate versus time characterization of this example would be. And we also can see directly that if we were to calculate the area under this curve, okay, so the area under this curve will give energy. Okay, so that is a straightforward mathematical relation. So let's look at it. The average HRR. Okay, so here we have two graphs showing two different average HRR behaviors. Okay, one of them, which is the orange one, this orange one is more elongated, which means it is more dispersed in time, whereas the blue one is taller, which means it is less dispersed in time. In terms of area, both these two areas are equal. Okay. So what we can say here is that energy content is same for both the cases. However, the blue case is more severe because the same amount of energy is released in a very short amount of time. Okay. So in the blue curve, the total energy has been released in 10 minutes, whereas in the orange curve, the total energy released is in 30 minutes. So from that point of view, the average HRR is much higher and this fire is much more severe compared to the other. So blue fire is more severe than this one, which is less severe. Let's look at one more example. This is an example where we have multiple materials. So the previous example considered only a single material. So here a storage room has 10 kilogram of wood. The calorific value is given here. 50 kilogram of gasoline, again calorific value is given, and 60 kilograms of diesel. Okay, these are the three materials which are stored within this storage room. First, we are asked that what is the total energy that can be released during a fire, which means we have to calculate the net energy content. Further, it is asked that if a fire that happens here lasts for 30 minutes, what will be the average HRR? So as earlier, the total energy content will be 10 kilogram of wood multiplied by its calorific value plus 50 kilogram of gasoline multiplied by its calorific value plus 60 kilogram of diesel multiplied by its calorific value. So the total energy content comes out to 435 gigajoules. Now this 435 gigajoules of energy is released in 30 minutes. Hence the Q, which is the average HRR, is 435 gigajoules divided by 30 times 60 seconds. So it comes out to be 241 megawatt. Okay. So we can already see that when we were burning 100 kilogram of wood, the fire severity or the average HRR release was much lower. In this case, since we have added two petroleum products which have a extremely high calorific value, the average HRR has increased drastically. So from here, we can conclude at least that the severity of this particular fire is more than what it would have been in the previous example. So, what we have seen is how to calculate average HRR, but as we saw in the previous slide, just the average does not give us a complete picture. Okay. And the other thing is that it's not that a fire will burn at a constant rate at all the time. So, from that point of view, let's look at a little bit more detail about the time versus heat release rate graphs. Now, let's look at this from a physics point of view. So, first we focus attention on the right hand side here. So, during initiation of fire, there is a small flame or a spark that has started, that is say time t equal to t naught, which is the initiation time. At this point in time, assuming that there is no lack of oxygen, the fire will spread on the surface of the item which is burning. It can be a sofa, it can be a table, or any other thing that can burn. So, which means the fire is growing in size. Okay. So, the amount of visible flames will increase and the fire is growing, and this phase is called the growth phase. Soon what will happen is that the flames will engulf all possible surfaces which are directly available, okay. And now there is no more possibility to increase the surface area where fire is occurring. In that case, this is the maximum possible burning rate which is linked with the maximum possible burning surface that would have been achieved, and hence the heat release which was increasing in the growth phase will stabilize. Okay. It will reach a peak value which is called the peak HRR, and for some time this will continue to happen, which means the peak will sustain, or the peak HRR will be achieved for a certain duration, which is called the sustained burning phase, right. So, time Tp is the time to reach the peak HRR, and then there is a sustained burning phase. After burning for some time, the surface area available will begin to reduce. This is because the item available has begun to shrink in size because it has been eaten away by the fire. Okay. So, this is when the decay phase starts. So, decay phase starts say at time Td, peak HRR is the initial HRR, and then it will decay. Finally, the fire ends, which is time T end, okay, and the HRR which is coming out of the fire becomes 0. So, from an HRR versus time behavior, what we see is that there is a growth phase, there is a sustained burning phase, there is a decay phase. A lot of experiments have shown that in the growth phase, the HRR versus time can be modeled using something called a T-squared fire model. Okay. So, what is a T-squared fire model? T-squared fire model simply implies that heat release rate, which is Q, can be written as a number alpha, which is an empirical parameter, multiplied by T squared, okay, where T is the time from ignition. Now, the value of alpha, which is a growth constant, okay, this is empirical and it has been determined through several experiments, and the table here gives the value of alpha, which is in this case we are calling alpha g because it is a growth phase constant. Okay. So, for slow burning fires versus medium versus fast versus ultra fast, so this is what we identify or classify the fires with, okay, and we will see which kind of fires can be called slow, medium, fast or ultra fast. But for them the rate constants alpha g are defined like so, okay, which means that the growth phase we know how to model now using T squared. Okay. Once the growth phase has completed, it reaches a Q peak, which is the peak heat release rate, and the decay phase, generally there are two options to model. One is we model it in the same way as a square term or as a quadratic relation. In that case, Q dk also is some constant alpha d times t squared, where alpha d is the decay phase constant, again determined experimentally. But from a more simplistic point of view, the decay phase can also be modeled as a linear decay to 0. Let us look at how the fire classification happens in terms of the slow, medium, fast or ultra fast rates. Okay. So, you will notice that here the units are different. Okay. That is why the numbers may look different, but they are exactly the same that we have in the previous to previous slide. It will be a good exercise to check these numbers. Now, for slow growth rate, it is generally applicable to wood type of items, which is like furniture or paper, so mostly cellulosic material, and these are densely packed wood materials. Densely packed means they are placed close to each other. Okay. That is a slow HRR fire. And on the graph on the right, the lowest graph here, this represents the slow growth rate of a fire. So, on the y axis here we have heat release rate in megawatts, on the x axis we have time in minutes. So, you see that slow growth rate implies that after 1 hour, the peak heat release rate has reached about 30 megawatts. Next is the medium. So, in medium we have solid wood furniture, but also we have a small amount of plastic. Okay. And generally plastic is derived from polymers. Most of them have petrochemical background or origin. Hence, plastics have greater amount of calorific value as compared to wooden items. You may recall that for wooden items, the calorific value was 17 to 19 megajoule per kg, whereas for petroleum products, it was ranging from around 40 megajoules per kg. Okay. So, the medium fire is this one, the red graph here. We will see that medium fire reaches 100 megawatt in just 50 minutes. Okay. Then next one is a fast. Fast is when you have furniture with a moderate amount of plastic and or upholstery, which means we are further increasing the amount of combustibles which have a greater calorific value. Okay. So, the fast curve is this, where it reaches 100 megawatt in about 25 minutes. Then the ultra fast is for a fire which is consuming predominantly synthetic materials and petrochemical products, like most of the epoxies which are derived from petrochemical products. And we will see that this ultra fast reaches 100 megawatt in just over 10 minutes. Okay. So, this is a spectrum of T squared fire models that we can use to assess the growth rate of fire and eventually to calculate the heat release rate originating from a kind of fire. Let us do an example using this T squared fire. So, there is an office room which has about 200 kilograms of furniture. Okay. We know that for furniture which is cellulosic material, the average calorific value is 17 megajoule per square meter, 17 megajoule per kg. If a medium T squared fire happens here, okay, and the peak HRR is given as 9 megawatt, estimate the total time of burning. If we go back to the HRR versus time graph, and we have a growth phase and a sustained burning phase. Okay. Now, what we are given is that this Q peak is 9 megawatts, that is given. We have to find out the total time of burning. Okay. Now, since we are using the T squared fire model, what we also know is that in the growth phase, Q can be written as alpha g times T squared. And for a medium fire from the previous slide, we get a value of alpha g, which is the growth phase constant, empirical constant for the T squared model. Okay. So that comes out to be 0.0117 kilowatt per square meter. So now we know alpha g, we know the Q peak. Okay. So we know that the time taken to reach this peak value can be calculated. Okay. So we put for Tp, Q peak is 9 megawatt divided by alpha g, which is 0.0117 kilowatt per second square root. So when we calculate this, we get 877 seconds. So we know that 877 seconds is the time to reach 9 megawatt for a medium fire. Okay. Next thing, we would like to calculate the energy released during the peak phase, during the growth phase. Okay. Now this energy is simply the area under this curve, which is the shaded area, and we know that for a parabola the area would be this Qp Tp by 3. Okay. Qp times, this is Tp time to peak, this is Qp, alright. So the total area that we get, or the total energy that we get, is 2631 megajoules. Okay. Now this 2631 megajoules is less than the actual total content of the room. Okay. So the total energy content of the room is 200 multiplied by 17, which is 3400 megajoules. So what we also know now is that during the growth phase, the entire energy content of the room would not have been finished. Hence, the fire will continue to the sustained burning phase. Okay. So the fire will continue to the sustained burning phase. And we also know that the energy available for the sustained burning phase is 3400 minus 2631. Okay. So that if we divide by the average HRR after that, which is this peak one, okay, so that will give us the total time of burn. So total time of burn will be time to reach the peak, which is 877 seconds, plus time of sustained burning. Okay. So overall it comes out to 16 minutes. What we have assumed here is that the decay phase is sudden. Okay. So there is no linear or quadratic. Okay. What we have assumed is growth phase, sustained burning phase, and decay is sudden. Okay. If we want a more accurate model, we can also consider the decay phase as linear or as quadratic, as we discussed earlier. However, from a design point of view, this particular assumption is on a conservative side because it gives a more severe fire as compared to a slow decay. Now from heat release versus time, we go to temperature versus time. Okay. So similar story is true here. Okay. There we were looking at the amount of heat or rate of release of heat. Here we are looking at the compartment temperature. Okay. Now we will differentiate between two different types of fire curves. First we discuss something called a real fire curve. So this is the temperature versus time behavior that is expected during a real fire, and overall it follows the same principles as that are followed for the HRR versus time, which means that there is an ignition, then there is a growth phase. So this is the time, the ignition and smoldering phase, which is when the amount of flames are slowly increasing. Okay. Then comes a growth phase. Okay. The growth phase can be very steep, which means very fast, or slow depending on the placement of the combustibles and also depending on the nature of combustibles, nature of openings, etc. Then there is a sustained burning phase, which is when temperatures would stabilize, okay, to say 800, 900, 1000 degrees Celsius depending on the situation. And then once the combustibles are finished or the oxygen supply is no longer available, there will be a decay phase. Okay. So this is a natural fire curve which will have ignition and smoldering, growth, sustained burning and decay. Most of the life safety operations needs to be finished within the ignition and smoldering phase, because if people are not evacuated after the growth phase, the temperatures become too high that the conditions become untenable for people. So if fire alarms and sprinklers, they need to operate during this phase. Fire extinguishers, if someone is trying to use, it has to be done here. Calls to the fire stations need to be made here. Evacuation, very high priority, has to happen as soon as possible, sometimes also called the golden period after a fire. Right. Compartmentation strategies, this is something we will discuss more about later. That will have to begin to become effective at this point in time. And ideally, firefighting should also start around this time, because the greater is the size of a fire, the more difficult it becomes to tackle for firefighters. Okay. And somewhere here, after the initial smoldering, the growth phase in most of the compartment fires can be very steep, okay, which means in a very short amount of time, the temperature rise will be quite high. Okay. So if such an event happens, this event from a compartment fire perspective is also called flashover. And in time versus temperature, there are two zones which are defined in terms of time. One is a pre-flashover time and second is a post-flashover time. Okay. In pre-flashover time, what we are saying is that all the life safety operations need to happen here. Right? And temperatures are generally small. People have to be evacuated during this time. Once fire crosses the flashover time, okay, that is when structural fire safety becomes extremely important. Okay. During the pre-flashover, temperatures are generally not high enough for structural members to take any serious damage. However, in the post-flashover regime, the structural fire safety becomes important, and this is where another standard fire curve is defined. Okay. And we will discuss in more detail later that all the fire ratings that we discuss about structural members or even for non-structural members, these are derived from the standard fire curve. For now, we will just notice that the standard fire curve is designed in a way that it starts around the growth phase, which means the initial steep growth in temperature is captured by the standard fire curve. That is one characteristic. The other characteristic is that it is an always increasing graph. There is no decay. Okay, so a real fire curve will have a decay phase, whereas standard fire curve keeps on increasing. The temperature keeps on increasing. Now, to look at what flashover is, let us look at a small video. Okay. So, we will discuss as we go along, but this video is made by the Oak Ridge Fire Department, and we would like to see how flashover happens in a compartment. So, here we have a compartment where a fire has been ignited at one of the corners. You will see a small flame. Okay, this is the initial ignition and smoldering phase of a fire. This is where temperature as well as the heat release rate is very gradually rising. And as of now, the mode of spread of fire is by proximity, which means if an item is close to a flame, it will begin to catch fire. Okay. So the fire was incidented or initialized at the edge there was a waste basket, that is where the fire was started. So the first items that will continue the fire or that will catch the fire next will be the two sofas or the couches which are kept next to the fire. Okay. So it's a fairly slow growing fire. In about a minute, now the couch or the sofa has caught fire, which were kept next to the source of fire. But items which are away from the original origin of fire, which is the other sofa, there is a table lamp, center table, these are as of now not affected. Okay. What we will also notice is that there is a thick layer of smoke forming on the top surface near the roof. Okay. So this fire is emitting smoke, hot gases, and we know that hot gases rise up due to buoyancy. So these hot gases are getting accumulated on the ceiling. And as more and more hot gases are released, we will see that there is a layer of the thickness of a layer of smoke layer forms. Okay. Smoke also begins to go out. But now you can visually see that there is a smoke layer on top and a clear zone on the bottom. Okay. So from the top, hot layer and smoke is going out. From the bottom, fresh air is coming in. For the initial part of a fire, this can be seen as a two-zone fire, where one zone is the smoke layer, hot gases going out. The other zone is the free zone below, from where fresh air is coming in. Okay. And the line that visually separates these two, this is sometimes called a neutral plane. Okay, because below the neutral plane, pressure is going inside, and from the above it is outside. Now you will see that some fumes are coming out of the sofa. Okay. And eventually the hot gases and the smoke that is trapped on the ceiling, okay, that begins to radiate energy all over, and suddenly the entire room catches fire. Okay. So this instant when the entire room catches fire, this is what is called flashover, and it can happen extremely suddenly. Okay. So what we saw was, now we can write some conditions which are necessary for fire, for a flashover. Okay. One is sufficient amount of fuel should be available. Second is sufficient amount of oxygen would be available. So these are anyway necessary conditions for a fire, which means a fire should sustain, and these, you will recall that these are part of the fire triangle or a fire tetrahedral. The most important part for a flashover to happen is that the compartment should be able to trap hot gases. Okay. So the main reason for flashover to happen is that there is a ceiling on top where these hot gases are getting trapped, okay, and eventually it is radiating back. So we have a compartment where on the top there is a smoke layer or hot gas layer. Okay. Maybe it is happening due to a fire from this side. What happens with time is that this gas layer gets hot enough that it begins to radiate heat throughout the room. Due to this, the other items which may have been there, they get heated beyond their ignition temperature, and suddenly the entire room catches fire. Okay. And this instant or this short amount of time during which a localized fire becomes a full room fire, that is what is called a flashover. So one of the necessary conditions for flashover is that compartment should be able to trap hot gases. Geometry of the compartment also plays an equally important role. So if geometry is such that hot gases are not able to radiate back, or there is a mechanism to transport these hot gases outside, okay, in that case again flashover becomes less likely. So for single compartments, Thomas did a lot of experiments during the 70s and came up with an empirical relation for critical heat flux or critical heat release rate, okay, purely based on geometrical parameters. And the idea is that if the expected HRR is greater than this Q flashover which is coming from this criteria, okay, then one can expect that a flashover will take place in the compartment, okay, and hence the firefighting or fire mitigation strategies have to be planned accordingly. And the beauty of this relation is that it is very simple, it has only geometrical parameters, okay. And here AT is the total internal area of the room, okay. AV is the area of the opening or the vent, and HV is the size of the opening. Okay. We will understand this in better detail through an example shortly. One thing which is also worth noting here is that something called ventilation factor, which is defined as AV times square root of H divided by AT, which in a way is appearing here. Okay. This is a very important factor from a compartment fire point of view, as most of the heat release rates can be linked directly with the ventilation factor. Okay. And since this is an empirical relation, on the right hand side we have everything given in the units of meter or meter square, and the flashover HRR that comes out in the units of megawatts. Now let us look at this example for flashover in a compartment. So earlier we did an example where fire lasted for 16 minutes with a 9 megawatt of peak HRR. Now if we say that that kind of fire happens in the compartment which is shown here, we need to estimate whether a flashover will take place or not. Okay. Okay. So let's start with the compartment dimensions. We have compartment length, breadth and height which is given. So 4 meters, 3 meters, 3 meters. There is one window which has length of the window as 1.5 meters and height of the window HV as 0.8 meters. Okay. So area of the vent or area of the opening is simply L times LV times HV, which is 1.5 times 0.8. So it comes out to be 1.2 square meters. The total internal area is the area of all the internal surfaces of the compartment. So it is length time breadth times length time height plus breadth time height whole multiplied by 2. So that comes out to 66 square meters. Now we have all the information to be put into the Thomas flashover criteria. So we have QF is equal to 0.0078 times AT, which is 66, plus 0.38 times AV, which is 1.2, times square root of HV, which is 0.8. So from here we get QF as 0.92 megawatt. Now this 0.92 megawatt is less than the 9 megawatt peak HRR that we were given. Hence we can conclude that the compartment will experience flashover. Okay. And since we know that we were using this T squared fire model where Q is equal to alpha times T squared, we can also calculate the time to flashover. Okay. So we can simply put here this 0.9 megawatt we put as Q, alpha is known because it is a medium fire. From there we can calculate TF, time to flashover, as 280 seconds. So this is how we can calculate whether flashover happens in a compartment and also the time to flashover. So we have discussed about fire load energy density, which is FLED, and TT, which is the time temperature graph. Okay. So we have seen there are empirical relations for HRR versus time. Okay. For temperature time, we have seen the standard fire curve, we have seen the natural fire curve. Okay. There are also these very popular Swedish fire curves which have growth and decay phase both and can be used for design. Nowadays it is also very popular to use advanced calculation methods. One of them is fire dynamics simulator or FDS. This has been developed by NIST in the US, okay, and it is a CFD code that can be used to calculate fire temperatures. Then the Eurocodes provide a method to calculate parametric fire curves. We will see this in a little detail shortly. Okay. And then among all of these, when we standardize, we saw that for the post flashover scenario, the standardized fire curve is this standard fire curve. The equation is given like this. Okay. We will see how it looks like. And one of the standards which specifies this is the ISO 834 standard. Okay. There is also a similar graph or similar time temperature standard curve, which is ASTM E119 curve. Okay. And the most important part here is that all the fire ratings are derived from the standard fire curve. Okay. We will discuss more on this also. These are the different standard fire curves that one can use. Okay. The most common, as I mentioned, is ISO 834. Okay. So that has been plotted here in the blue graph. Okay. This is the ISO 834 fire curve. A similar standard curve is the ASTM E119 curve. It is given by this equation, okay, and it is shown by the blue curve here. Okay. So you will notice that the ISO 834 curve after about 1 hour is generally below the ASTM curve. Okay. Then for external members or walls, there is also an external fire curve which is less severe, which is this blue curve. Okay. And for maritime industry, where a lot of structures deal with petroleum or petroleum products, one of the most important curve is this hydrocarbon curve. Okay. So that is this purple curve. What you will notice is that the growth rate is extremely high. Okay. So it reaches very high temperatures in a very short amount of time. And also the maximum temperature of burn is greater for almost up to 3 hours compared to any other standard curve. So ASTM E1529, this specifies this hydrocarbon curve, which is given by this equation. In all of these, there is a term of T naught. This T naught is nothing but ambient temperature. Okay. So T naught is ambient. And generally this ISO 834 has defined this ambient temperatures as 20 degrees Celsius. However, we can take it as per our requirement. Now another aspect is that if you want to characterize fire in more detail, which is, say, if you want to use parametric fire curve, okay, we need to be aware of the FLED or the fire load energy density estimation. Okay. So this table here shows the FLED estimation from several studies, okay, for different countries, and this table is meant for office buildings, which means year wise we can see how the fire load energy density in office buildings has changed. Okay. And you will see the values here. Initially they were around, the mean FLED was around 300 megajoules per square meter, whereas in 2015 it has become almost 4 times, which is around 1300 megajoule per square meter. So which implies that the same building would have had lesser fire severity few years back or few decades back, whereas now the fire severity will be much higher. So how do we use that information to come up with more performance based fire curves? Okay. So when we were discussing the fire curves earlier, we said that there is a natural curve, okay, which is the blue graph here, natural graph. Then there is a green graph, which is the standard fire curve. So the ISO 834, okay, so ISO 834 or this ASTM E119, that is this standard fire curve. But then the Eurocodes give us another way to define a parametric fire curve. The main difference here is in the decay phase. Okay. So the standard curve is an increasing graph, there is no decay phase, whereas using this Eurocode parametric curve, we are able to incorporate a decay phase in the temperature versus time of a fire, which is more closely related to the natural fire curve. Okay. So, the calculation method is given in annexure A of EN 1991-1-2, and we will just go over it in a glimpse. So, the total design fire load density is first calculated. Okay. This is based on the characteristic density, which is given in terms of tables, we will see that shortly, multiplied by several factors. Okay. This is step 1, is the design fire load density. So, M is a combustion factor. For cellulosic fires, it can be assumed as 0.8. For say petrochemical fires, it may be higher. Okay. Then there are 3 factors. One is delta Q1, delta Q2 and delta N. So, delta Q1 is considering fire activation risk. Okay. So, delta Q1 itself comprises of 2 parts. Okay. So, we will see that this table gives us the factors of delta Q1 and delta Q2. As the compartment floor area increases, the perceived danger of fire activation increases. So, this factor increases. Since these are from Eurocodes, these commas imply a decimal point. So, this 1,10 is effectively 1.10. And for the fire danger activation risk, you will see that it is dependent on the type of occupancy. So, occupancy of where you have fireworks or paints, the fire danger activation is high, so then the multiplication factor is high. Okay. So, that is how the one is the actual measured, but then there is a risk associated with it, and these risk factors are incorporated as these multiplication factors. Now, for delta N, this is a measure of active firefighting measures. So, with delta Q1 and delta Q2, we were incorporating the risk of fire activation, which means how likely a fire will happen. Delta N incorporates how likely a fire will be suppressed during the initial phases, because there is a fire fighting system. Okay. So, for example, if we have automatic water based fire extinguishing system, the value of delta N1 will be 0.61. Okay. So, these values generally will be lesser than 1, because if there is a good firefighting measure available, the risk reduces. Okay. So, for delta 1 and delta 2, delta Q1 and delta 2, these are generally greater or equal to 1, because higher risk means higher numbers here, whereas delta 1 will be generally less than 1, because this is related to firefighting measures. So, if there are better firefighting measures, delta N will be less than 1. Now, the last parameter we have to discuss is QFK, okay, which is the characteristic fire load density. So, we saw a few slides back that it is possible to do surveys and to come up with the average or these kind of statistics on the fire load energy density. Generally, one can plot the histogram of surveys, right. So, we do fire load energy density calculation and we plot a histogram. From histogram, it gives rise to a probability density function. Okay. And it has been observed that for characteristic fire load or the fire load, generally a Gumbel type distribution is what it follows. Okay. And the average and the 80th fractile is given here. So, average is a the statistical mean or the arithmetic mean, and the 80th percentile. So, for fire load energy density QFK, it is recommended to take these 80th percentile values, okay, and for different kind of dwellings, different values are given in megajoule per square meter. So, once we have this, so the QFK value can actually come from an actual survey or from a Eurocode table, which is this. Then based on the firefighting measures and fire activation risk, we will find out these factors. So that gives us the total design fire load. This is total design FLED. Step 2 is heating phase calculations. So if you recall, in parametric fire curve, we are trying to develop time versus temperature graph. There is a heating phase, there is a decay phase or a cooling phase. So step 2, we are doing heating phase calculations. So in heating phase, the gas temperature theta G is written as T naught, which is 20 degrees Celsius, plus this expression, okay, where this T star is a dimensionless time in some way, and here gamma is again a normalized opening factor. Okay, O is the opening factor. So O is the opening factor that we discussed earlier, and other terms are similar, right? So AV is the total area of vertical openings that we already saw earlier. H equivalent is the weighted average of window height. So if you have multiple windows of different heights, it is an average. Okay, and AT is the total area of all enclosures, wall, ceiling and floor, including openings. Okay, so we don't have to discount the openings in this total area because that is being considered in AV. Okay. And it is possible to show that when this gamma is equal to 1, in that case, this equation corresponds to a standard fire curve, which means in that case the heating phase temperature will be same as that given by a standard curve. Now, what this curve also allows us to do is to be able to account for different B factors, where B is defined as this, and rho C lambda is nothing but thermal mass. So the thermal mass can be calculated, thermal property of all the enclosure of walls. So it will depend on the material of the wall, thickness of the wall, etc. So from all of this, first we calculate T max, which is time of burning. Okay, so time up to which heating phase will be there. So that is what this T max is. Now T max, depending on the opening factor, will be either T limit, which is if the fire is fuel controlled, or equal to this value, which is if the fire is ventilation controlled. So if we have opening sizes which are large enough such that enough oxygen and air supply can be ensured throughout the burning duration, then it is a fuel controlled fire, which means the growth and decay of the fire will be governed by how fast and how much fuel can burn. If, however, the opening sizes are small so that sufficient amount of oxygen is not available for the fuel to burn, that will be a ventilation controlled fire. Okay. In this case, initially the fire growth will be governed by fuel. However, once the windows or openings begin to create a restriction on the air movement, the fire will become ventilation controlled. Okay. And this T limit in case of fuel controlled fire is again linked to the fire growth rate. So for slow fire growth rate, T limit is 25 minutes, medium growth rate 20 minutes, and in case of fast it is 15 minutes. So like this we can calculate. Now this should be step 3. So step 3 is cooling phase calculations. Okay. So what we have calculated so far is we have calculated this theta G, and we have also calculated T max. Okay. T max is the time up to which growth happens. After this, decay will be there, and the Eurocode parametric graph, parametric fire, models decay as a linear decay, okay, not as a quadratic decay. Now, depending on the value of this T max star, there are different expressions for the decay phase, but based on that it is possible to calculate. Okay. So please try out an example yourself of calculating this. I will show you the results of some simulations that were done here. Okay. So, for different FLED values ranging from 742 to 3000 megajoule per square meter, different parametric curves were derived. And the other variable here is the opening factor. So, one variable is the FLED, one variable is the opening factor. And these graphs here are plotted with respect to the standard curve. So, the red one is the ISO 834 fire and the blue one is the ASTM E119 fire. Okay. So, we can see some simple differences. So, one is that, say, if we consider this 742 megajoule per square meter fire. Okay. So, when the opening factor is 0.036 versus double of that, which is around 0.68. Okay. So, when opening factor is small, the maximum temperature reached is small. When the opening factor is large, maximum temperature reached is also large. Okay. So, if enough fuel is available, smaller opening factor implies a ventilation controlled fire, and hence the temperature, heat release, and hence the temperature is limited by that. Whereas if sufficient oxygen is available, the fuel achieves its full potential in terms of heat release, and similarly the temperature increases. This is a similar sort of calculation for a different set. Okay. So, this one is for, say, office buildings, this one is for other type of buildings that were done in this paper. You can have a look. So, finally, what we can conclude is that fire load estimation requires primarily 3 steps. One is a survey. We identify the buildings, classify the occupancy, catalog all the combustible items with different materials. Basically, we create a full inventory of what materials are available. Then we need a way to measure their mass. Okay. It can be through direct weighing if we have a weighing scale. It can also be an inventory method, which means if there are standardized materials which have been pre-weighed, which are available, that can be available as a list and can be directly taken from there. Then we do a sample collection. So, for each type of different material, we collect a sample. The reason we need a sample is we need to calculate its heat release rate or the total energy content. Okay. So, this can be achieved through these equipment. So, the most common being cone calorimeter. Cone calorimeter is like a workhorse of fire engineering. So, I believe you are also learning about explosions in this. So, for explosions, explosion vessels are what characterize different characteristics. Similarly, for combustibles, cone calorimeter is what characterizes different things. This is an image that shows a cone calorimeter which is available at IIT Gandhinagar. So, this cone calorimeter, this is the overall equipment. This is the test chamber, and the test chamber is enlarged view is shown here. So, what is here is that this 3 rods, these are connected to this sample holder. So, this is a sample holder. This is connected to a load cell at the bottom which measures the mass. Okay. And this particular thing, this is the cone heater. It is a frustum of a cone. It provides an incident heat flux on the surface of the material. Then there is an igniter which begins the combustion in case it catches fire. So, when it is burning, this mass balance is continuously measuring the mass loss of the sample. So, later on we are able to see the mass versus time graph. The other thing which happens is that these hot gases, these are linked to this fume hood which goes to a gas analyzer, and from the exhaust fumes, the amount of oxygen, carbon monoxide and carbon dioxide, at least these 3 are measured through spectrometry. The amount of oxygen present eventually gives us the heat release rate through oxygen calorimetry. That is the basic principle how this works. Okay. So, through this we are able to measure the mass loss rate and the heat release rate of specimens. Both of these things are required for calculation of the overall heat release from a compartment. This is a photograph that just shows what happens to the sample after it has been burned. So, in summary, fire load energy density characterizes the amount of fire load within a compartment. Okay. It is measured in megajoules per square meters. Fires are characterized in two ways. One is HRR versus time, one is temperature versus time. In HRR versus time, we saw the T squared fire model. In temperature versus time, we saw the natural fire curve, the standard fire curve. Standard fire curves we saw of different kinds: the ISO 834 curve, ASTM E119 curve, the Eurocode external fire curve, and the hydrocarbon curve, which is ASTM E1592. In structural systems, we typically require the time temperature curve of the fire. So for us, it is generally sufficient to know the temperature to be able to do the structural calculations. Although if we are doing more advanced calculations, in that case heat release rate is also required. We saw how we can take fire load, energy density, and create time temperature curves using the Eurocode parametric fire curve. Okay. It is also possible to do advanced calculations through fire dynamic simulators. However, that is not the purview of the current course. So the way forward is, we have seen how to characterize fire temperature. We need to now know how to calculate structural temperatures, and eventually we need to go towards structural behavior and structural ratings.